Valen? Valen, go on, please.
We are Science for Life. We are here to make the world a better place. We are the trusted ally of animal producers in Asia, Africa, and the Americas. We are here to create value with sustainable, efficient, and innovative products that transform challenges into effective solutions. Solutions for animal welfare, solutions for you. Smart and advanced products to take care of the productive development of animals. Natural alternatives for conscientious production and development. Functional additives to enhance productive performance. We are proud members of Illuma Alliance, a place where knowledge, technology, and innovation come together to forge a better world. Our innovation centers help us validate the safety, feasibility, utility, and sustainability of new concepts. Our international laboratory network allows us to provide ultra-precise and efficient solutions. Our pilot plants enable us to transform concepts into functional products. Our experimental farms offer precision in vivo utility testing. This is our ecosystem of skills, capabilities, and mindset. This is the ecosystem we make available to you in order to provide solutions for your animals and for a better world. We are Alura. Science for Life.
Well, good morning, everyone. Welcome to the Alura Looking Ahead third webinar in our four-part series of poultry food safety farm to table. My name is Manuela Mesa, and I'm part of the Alura's marketing team. Today, I have the pleasure to be your moderator on this webinar. Before we start, we would like to inform you that this webinar will be recorded and we will have time for questions and answers at the end of the presentation. Feel free to post your questions in the question box, and we'll do our absolute best to get to you as soon as possible. Together with me, I have Dr. Marcos Sánchez. Dr. Sánchez Plata is an associate professor, global food security and food safety at Texas Tech University. He received his PhD from University of Nebraska-Lincoln and has provided industry leadership and innovation in an extensive range of areas, including in-plant antimicrobial intervention, risk assessment in food safety management systems, and safety implications of new processing technologies. I'll pass the mic over to you, Dr. Sánchez. The stage is yours.
Thank you for the introduction, and thank you to Alura for the invitation. Please let me know if you can hear me right and if you are seeing the presentation. Okay, so good morning, everyone, and thank you for joining the session. To me, it's always a pleasure to participate in these webinars and kind of share some of the work we've been doing in the last 5 years on application of microbial testing to support the statistical process control management in poultry operations. So we call this an integrated food safety management because we're going to try to include the pre-harvest component with the processing facility and using quantification of indicator and pathogens to build up biomaps. The biomaps then serve us to collect sufficient data for establishing a statistical process control thresholds And this will help us in turn provide a risk-based management system for risk assessment in the poultry operation. While we're doing all this, I'm sure you have some introductions in prior webinars, but it's a regulatory component that is coming up. It's composed of 3 stages, 3 components. One is on the pre-harvest side, one is on the processing side with statistical process control, and finally one with a standard that we're waiting for USDA FSIS to publish in the near term. All of this is based on new developments on quantification technologies for pathogens like Salmonella, the definition of virulent-based genes on the strains of Salmonella that could become potentially an adulterant in poultry products, and then the approach of using the data collected in the plant to connect with pre-harvest settings for a more integrated food safety management. The presentation today is going to be focused on why we're using biomapping for these processes to develop baselines, what projects and parameters can we do in a processing facility for establishing this process microbial define the process microbial performance, where and when to take samples, who should run these tests, how to interpret the data, and some ways of visualization and management for application in your operations. Some of the slides are based on a guideline that came up in 2015, where USDA recommended companies to develop a process mapping using indicator bacteria, either total counts, total aerobic counts, the Enterobacteriaceae, coliforms, or E. coli. By collecting this data in different stages of the process, you kind of understand the performance of the whole system to reduce microbial contamination. Then the idea was to identify pathogens in the line by prevalence, and then try to correlate the pathogen levels in prevalence with indicator organisms. Using that information, establishing limits, usually set up with 2 or 3 standard deviations from the variation of the indicator organisms to establish an upper threshold for management. And finally, with these decisions, if you come up with an upper threshold internally for your facility, you will define actions that will be in looking at reducing the contamination on the process. We've done this with prevalence data. This is showing you a prevalence on the y-axis and a different dates on the x-axis on a facility. The size of the circle shows you the number of samples, as you can see at the bottom. And we establish a street light kind of system where we develop an upper threshold based on prevalence. That's the dotted line that you see on the chart. And it's showing you the dates where these the number of samples collected show us that we were out of control. So we initiated the process, that was 2017, and that this was looked at all the way until 2019. And you can see that we have some cycles, but then at the end, we start showing more control on the process. We added interventions to the facility, and you start seeing more on the green side on this system. We did this for different parts in the facility. These were wings. We also did it for whole chicken, for chicken breasts, for chicken legs, leg quarters. Chicken wings would tend to be your worst case scenario, and that's why we focus on that stage. So that was one way of using the prevalence data for Salmonella for statistical process control. The using indicators can work. Unfortunately, the correlation between the indicators, as you can see here on the y-axis, on the aerobic plate counts and Enterobacteriaceae against Salmonella counts, we did this comparison with Salmonella quantification, is not perfect. As you can see, the correlation is very low. And this shows that you can have samples with high levels of indicators, but without pathogens, or samples with low levels of indicators with sufficient pathogens in that sample. So there's not a perfect correlation, but in any case, measuring indicators can still give us a reading of the process, a diagnostic of the process itself. I've shown this in prior webinars where if we have one chicken contaminated with low levels, the sampling program we have with the whole carcass rinse, well, if we use just detection, it will grow this pathogen in low levels to a detectable level, and it will give us a positive reading on the sample. We don't know how much is there. However, if we have a loaded sample, for example, and we sample it the same way, the response will be the same with detection positive, but we don't know how much. If we do the same thing with parts, for example, with tenders, we need to take into account that there is a significant surface area increase in the parts, so we cannot compare side to side whole carcass samples with parts because the numbers are going to be different. You're going to have way more surface area to cover in parts, and the same thing goes with ground product because you're going to have a sample size dependency if you sample 25 grams versus if you sample 325 grams. So if you go into a facility, you can have different chicken samples, and they will have different loads of the pathogen. The risk assessment in this process, if we only base on prevalence, we will have 4 positives out of these 18 chickens in the sample. But if we look at it, there's a distribution of contamination, and these ones with the higher load will be the ones that could have some implications for making somebody sick, the ones that could survive maybe a cooking process, or the ones that could be transferred during the handling of the chicken, raw chicken, into other non-cooked products. So there's a distribution. So therefore, the risk assessment has to look at the distribution of contamination, not the prevalence, positive or negative presence on a sample. So that's why we are looking more into the range of distribution of the samples to define finally the presence of the hazard versus the risk associated with that hazard. How much salmonella is on a per carcass sample so that we can send it to the consumer. And this is all based on risk assessment. This is an old risk assessment. We're waiting for a new one to come up sometime this year from the FAO and WHO. But the idea is that every box here that you see on the Y scale, you have the probability of illness from 0 to 100 and the log dose that you need for make people sick. The black boxes indicate outbreaks where they have found the dose of the organism that make people sick. This is salmonella. So we're looking at a D50, or 50% of people get sick when you got more than 4 logs or 10,000 CFU per gram of a product. But if you start reducing those numbers, you reduce the percentage on the risk of making people sick. So for this, we developed a standard protocol that we have tested with several facilities in the US and outside the US for developing facility-specific baselines based on quantitative biomapping of pathogens and the indicators. We use the data at the end to establish statistical process control parameters, and then we use those for continuous monitoring of the facility. My goal today is to give you some of the insights into these studies. If you already have some data like this, or if you want to modify your program to kind of use this as a way of improving your program or enhancing your program to make more decisions based on the actual performance of your facility. It takes us about 2 weeks to plan the study for the logistics. About 10 sampling weeks is what I'm looking for to cover a significant variability between flocks and lots. 2 weeks of analysis for the data, and a total of 3 months for the whole study to complete. But this will give you a whole diagnostics of the program, of the facility, of the processing program you have. We try to use at least 5 different days. I prefer 10 different days during the 10 weeks. We look at lot and flock differences. We try to look at morning and afternoon shifts because there's effect in the shift. We have data showing that. There's accumulation effect in the facility. And we're looking at least 5 locations in the process to collect data for the diagnostic for the facility. We can increase the number of locations because sometimes we want to validate some of the interventions that we have included in the program. But at least I want 50 total data points for each location that I sample on these studies. We look at total counts or aerobic counts. Interbacteriation has been the indicator that we use the most. Coliforms and E. coli we haven't used much lately because the numbers tend to be very low, especially in the post-chill locations. And then we look at Campylobacter and Salmonella, not only prevalence, but also quantification. Prior biomappings that we have conducted, this look like this. You can see the counts of total counts on the y-axis, and then the location and the interventions with the little arrows here on the facility. As you can see, we have 3 to 4 levels of reduction of contamination with total counts in this facility. Then we run statistics. We use box plots because 50% of the data points are in the square, in the box, and then the black line in the middle shows us the median value of the data. And then you can see the variability of the data. Each circle is a data point that we use for this calculation. With this information, we're able to establish a mean of the process on each of the locations. We're able to run the statistics and determine statistically significant differences between locations. So we have one dirty area between the live receiving and defeathering. We have another area between rehanging and pre-washes, another level of contamination during the visceration and the carcass washing and disinfection, and finally another level during the pre-chilling interventions and cooling of the carcasses at the end. And we also have a fifth level, which is in the parts section. The same thing if we look at it from the Enterobacteriaceae perspective, a little lower levels of contamination, but we also see this variability and 3 to 4 very clear locations of contamination. The reason why we stop using coliforms and E. coli is because the levels in post-chill operations, because of the chemical interventions we use, tend to be very low, and we cannot do much statistics with those values, and that's why we're using total counts as an indicator. So we did this with indicators, and we established some levels of reduction from feather removal, from visceral removal and carcass washes, and then from cooling and chilling effect that you can achieve with the chilling operation. So where do we sample, when, and by who? Try to look at key processing steps. We believe that the places where you get the most information are the arrival. We use live receiving as a place where we collect samples. We look at recent DOAs, the dead on arrival birds that are in the loading area as a sample for that location. We have seen that there's a very nice distribution of the data of these live receiving birds, and they could be used as a connecting step with the pre-harvest assessment, because we can find out the level of contamination coming from the different farms. Then we look at the rehang location, which has been used by USDA FSIS for standard sampling. Key evisceration stages, where you have a specific carcass washes, disinfection, inside-outside bird washes for intervention applications. Of course, the chilling system to find out what happens with the whole carcass. And then we look at the parts, looking at skin on and skin off parts, and then treated or untreated parts at the end. And finally, comminuted products with ground products as our final sampling for our diagnostics. We have conducted these studies in some of US facilities. We look at low levels of chemicals applied in the operation compared to high levels of chemicals. You can see the live receiving data coming here, very narrow distribution there. So that's what we're saying, that it's a good location for connecting with pre-harvest. And then you can see in blue the boxes of distribution when we lower the chemical levels at the lowest levels, and in red when we use the chemicals at the regular levels of operation in some of the locations. So you can see the chemical use kind of narrows down the distribution of the information. This is total counts, but you can see that there's reductions are happening in some places, and in some places the reductions are not statistically significant. So using this approach, we were able to optimize the intervention scheme and reduce the use of chemicals in some locations where there's no much effect, and then optimize the chemical use in places where you get more reductions in the process. By doing this, we save some chemicals, and we optimize the process and kept ongoing reductions in the system. This is with Enterobacteriaceae, a little lower levels, but you can see the same trends, the same differences in some locations, but not significant difference in other locations. You can see here low chemicals in the wings area, using wings as the worst case scenario for parts. This paper has been published, so you can look at it with more detail with some of the information there. We have conducted these same studies in other countries. This is in Central America, where we've done biomapping in 5 locations, which are the minimum that we recommend doing in a facility for a baseline, which is live receiving, rehanging, post-evisceration, post-chiller, and then using the wings as the worst case scenario in a facility. In this country, we went to and sampled 4 plants that represented 80% of the production in that country. And so therefore, we kind of develop kind of like a national baseline with indicators, total counts on the left and Enterobacteriaceae counts on the right. We did this with a mobile type system for indicators. It was called MicroSnap. And then we compared that with the levels in the US, which you see in these boxes here. We did that the same thing in South America in a plant that doesn't use any chemicals. So the no chemicals used, you can see the difference here with the US data. This is the black boxes. The white boxes are with the US data. The US, the location without chemicals, you can see that the levels tend to be higher because they don't use much chemicals interventions, because they're targeting the European market. So how do we use and interpret the data? This is showing, for example, data collected for pre-chilling and post-chilling location in a facility that used PAA in the chillers or no PAA for the European market. So we can just look at the data like this in an Excel document, come up with an average, a standard deviation, and then we can use this standard deviation and come up with an upper threshold value for my facility. So we can do that straightforward in an Excel document, and we can come up with an upper threshold value for pre-chilling and an upper threshold value for post-chilling as my statistical process control parameter. Then we also look at visualization. For example, this is the same data, all the samples collected. In blue, you have with no chemical intervention. So you have the chiller pre and post chilling, reductions very low because there's no chemical intervention, just the rinsing effect of the chilling. But then with the chemical intervention, you can see the red reduction from 2.4, 2.5 logs all the way to 0.5 reduction. So 2 log reduction in the chilling with the chemical intervention. So this data not only serves as the diagnostics of the facility and the statistical process control, but also we can use this chart to validate my chemical intervention in the chilling tank. Something to understand is that the statistics tend to become complex when you start getting low levels because you go into non-normal distribution of the data. When you have that, you have to use non-parametric statistics, and therefore you have to work with a statistician to be able to analyze the data and come up with statistical significant differences. If we take the same data points and we look at them throughout over time, then you can see charts like this, where you have the little circles are each data point, and the squares that you see here are the average of each day of operation. So you can see in blue, the variability of the process, and in dotted lines, the upper thresholds and lower thresholds that we establish with a statistical process control. So you can see days where the control the facility is under control, and then some days where you have above the upper threshold where you're looking at out of control flux coming in. So you may be able to go and do some homework and look at the lot management and try to find out the root cause analysis on why those lots were coming loaded with more contamination than the regular ones that we have in the facility. So it could be maybe a rain issue, a fecal contamination, bedding issue, wet bedding in the chicken houses. Those type of things could be the root cause of some of those higher levels of contamination. And then when you look at the one treated with antimicrobials, you can see that the numbers are very low in that facility. So we need to understand that this is a process control. It's not a hygiene, it's a hygiene criteria. It's not a microbiological criteria. We're not taking action on the product. We're looking at the process to make it better for continuous improvement. Some of the new things we're doing is this mobile standard deviation, or we call it a sequential standard deviation, or XMR charts. What you can see is that every time you add a new data set to the system, it recalculates your thresholds. So it's an ongoing threshold determination for your process. And this is something that is more attractive for the poultry industry, because you don't have to do a big study, but rather you can do sample collection on a weekly basis, and then you start adding up and compounding those data points to calculate your upper and lower thresholds in your process. So here you have a live receiving and a post-intervention data points being collected, and how the upper threshold will be calculated. This was done with indicators and with prevalence data. What are we doing now? We're using RT-PCR methods, real-time PCR methods, for estimating. I don't call it counting, but estimating the load of pathogens in the samples that we collect. What it uses is that the PCR targets DNA fragments from the organism, the target organism, and then you compare this against the traditional most probable number technique. And the idea is that the more cycles the PCR system has to run, that means the less DNA target fragments are available in the sample. The less cycles you have to run, that means there's more target samples, and you can detect the pathogen. So a correlation curve has been developed by different companies, different systems for RT-PCR to use the number of cycles as an indicator of how many target DNA fragments are in the sample, and therefore we can quantify this testing. So all of these methods have been submitted for AOSC validation and proficiency testing. And even though they have significant variation, they can give us an estimate of the levels of quantification that you have on the sample. But as these methods will show, they have limits in the limit of quantification and the limit of detection that you have on the samples. Some of that data we have shown in different webinars, and we have shared this data with some of the regulators. If we look at just the prevalence information like this chart, in a facility, we're looking at the live receiving prevalence of pathogens, and the rehanging, the post-EVIS, pre-chill and post-chill data. We have reductions in this facility. If you go into the cut-up and deboning room, we have the wings with and without intervention. and the tenders with and without intervention to cover skin on and skin off samples. If we just do the prevalence, we can see this facility will have high levels of prevalence of Salmonella, which will be in trouble with the category system we have right now on category 3 for whole carcasses and parts. But if we look at the same samples that we quantify the Salmonella that is present there, and we use the y-axis on the left side, then we can see that the levels, even though they start between around 3 log with a variability between 4.5 and negative on the live receiving side, those numbers tend to be reduced by the removal of feathers, viscera, carcass washes, pre-chill operations and post-chill operations, and the levels on the actual samples that can become positive here tend to be below 1.5, 1 log of the sample. So therefore, then we get into the limitations of the RT-PCR methods on detection, because they tend to have limits of quantification, either 10 CFU or 1 CFU per gram of sample. But if we're looking at the risk assessment, definitely these samples, which are parts and whole carcasses, will have very low levels of Salmonella from the initial levels that we have when the process started. If we look just at the final samples that we can see here, the whole carcass, we got 50 samples, but only 8 were enumerable, which using the RT-PCR system. Most of the other samples were under the LOQ, the quantification level of 1 CFU in that method, in that study. Same thing with the wings, with only 12 enumerable, and then with the tenders, with post-visceration, with only 3 enumerable after the carcass intervention. So you need to be careful there, because even though you can do quantification, when you're looking at the final products, the current methodology doesn't give you it's not able to detect those very low levels of the pathogen in the sample. If we look back at the other study where we compared high and low levels of contamination, high and low levels of chemical interventions, then you can see the prevalence on the lines here. Blue is with low chemicals and red is with the high chemical levels. And then you see the live receiving of Salmonella levels here with a 3 log median in the data collection, some on the negative side, some under the level of detection detected by the detection methods. But then you can see that in the process itself, you have some outliers, but most of the samples fall under the 2 log, 1 log level of contamination with the pathogen itself, especially with the post-chill samples that we can see here. We see that increase in the prevalence and a little bit of more detectable in the parts area of the sample. So this is for Salmonella. So in that study, what we reported, and it's published, we use this scheme for reporting the data. If you got a negative result of quantification and a negative result on detection, then that is a negative sample. But if you got a non-countable sample, but still detectable, we come up with a 50% of the lower detection level as a way of having a count for that sample that we know is positive, but we were not able to quantify. So we established that value at 0.3. The paper explains some of the methodology for why we did that level, and that allows us to actually get an average for a statistical analysis of the pathogen load with the samples that are non-detectable, that are non-quantifiable, but still detectable in the system. We have used several RT-PCR technologies. It's another biomap using a methodology that has a lower detection quantification level of 10 CFU per gram. This is the biomap in a facility with some of the data points there, 50 data points collected. You see that they have a much better incoming level of Salmonella in the facility. However, it's 90% on the prevalence on the incoming levels of detection. Then it goes down in the chilling tanks. We compare chillings with and without neutralized BPW, and we didn't see much difference in between the two. Then we go into parts, wings, and treated wings, tenders, and treated tenders, and you can see that trend. But with this method, with the quantification, we can see that it's detectable still, but not quantifiable because it's under that 10 CFU per gram or 10 CFU per mil of sample of detection. Again, for that other methodology, we have a different lower detection level that we use to calculate, and this has also been in the publication at the moment. When we look at those plants in the other country that we mentioned, we have quantification here in the boxes, and then we have prevalence in the line. You can see the high prevalence coming in, and then lower in the chilling tank, but it coming up in the parts area with the wings. When we look at the quantification levels, you can see that the level is about 3 logs, 3.5 logs. Then it goes down in the rehanging, post-EVIS. Not much reductions here because they don't use much chemical interventions, but they definitely use chemical interventions in the chilling tank. And that's why you see the significant reduction here. Probably they will have to work on some intervention for the parts at the end of the process. And then when we benchmark with this, with the US data that we have, we can see that this facility that uses chemicals in Central America is comparable to the US facility. When we look at the other facility in South America that doesn't use chemicals, we can see that we have a better control probably on the incoming salmonella. One of the facilities had no salmonella detectable in the pre-harvest. We're working on them to find out their secret, to find out why that happened. That lowered the average in this study. But this shows that without chemicals, you can also have some level of control on the process just by the recent removal and hygienic processing that you can have. However, this tends to show up in the wings part of the facility where you have 30% prevalence, and even though the mean is on the detectable level, you have some samples that are on the high end of pathogen contamination. When we benchmark it with the US, we see that they are in the lower end on the salmonella levels compared to the US facilities, but we go down with the chemical interventions, and then we are equivalent in the post-chill parts and better in the wings part compared to this facility. So one of the problems we have with this level of quantification and level of detection is this. A lot of the samples some of the samples are enumerable, higher than the level of quantification, but a lot of them are under the level of quantification, but it's still detectable. And some of the samples are going to be non-detectable, non-quantifiable. That will be the negative samples in this location. So that's what is the challenge with the sampling location. So with Alura, we're working on trying to come up with a partnership so to offer the services to processing facilities that would like to work on this approach. We will design a sampling program for your facility and look at data on the plant for diagnostics, develop an indicator for pre-harvest connection, and then maybe test some of the interventions that could be applied in pre-harvest to lower that incoming level of contamination. Some of the projects that we have considered and we can discuss with some of the interested facilities will be looking at ranking of the flocks and for pre-harvest farm management, looking at interventions in pre-harvest, either probiotics or antimicrobials that you can use on pre-harvest and their effect on the level of incoming salmonella coming into the facility. We can look at not only the levels, prevalence, and also the loads, but also potentially the serotypes that are being arriving into the plant and the virulence genes of those pathogens. We can look at continuous improvement on farm management, looking at the good farms and the bad farms, learning from the good farms and taking measures on the bad farms for continuous improvement. We can customize the process. If we know that the flocks are coming from a farm with challenges, we can have a different scheme of processing in the plant where maybe higher levels of interventions can be used so that we can lower the overall levels of contamination, or we can schedule the flocks with problems to be sampled in the later shifts of the facility so that we have cleaner flocks processed earlier in the facility. We can validate interventions, either physical or chemical interventions in the plant. We can develop microbial baselines for the plant-to-plant comparison when companies have different plants and they want to find out which one is doing better things. We can do that. We can come up with baselines for sanitary dressing procedures to find out if either the workers or the equipment that we have is giving us a better hygienic product. We can look at equipment adjustment, size, uniformity performance, baselines to compare line speed modifications if you have new poultry inspection systems, and the overall process continuous improvement for your facility. A little example that we can show here is we went to a plant and we took boot swabs in the farm, and then we look at the rehang, post-EVIS, post-chill, and wing samples in the plant. So with these boot swabs collection 2 weeks before processing, we were able to establish an upper threshold value of 4.9 log CFU of salmonella at the farm for 400 mils of rinse of the carcass at the farm. This is boot swab and this is carcass rinses. So with this, we're able to rank the farms that are above this threshold and below this threshold to determine if they have, what are they doing different so that the levels of salmonella are different. You can do it on every other location. The goal of this process is that we can risk rank this facility. We can determine the chicken houses that we need to investigate why their levels are higher than the other ones. And then the chicken houses where the levels are so good that we can learn from them to find out why their levels were low. We can also send the farms with the cleaner levels of salmonella to be processed first, and the farms with the higher levels of salmonella to be processed last, or maybe with higher chemical intervention levels in the facility. What we're looking for is a partner in the industry so we can develop something like this. This heat map shows you different flocks in a chicken house, on a chicken farm, on a per year basis. This is 3 different years. This was developed using prevalence data on salmonella, looking at how many houses were positive out of a chicken farm. So, but we can do this now on a chicken house level with quantification, and we can identify chicken houses that routinely give me low levels and chicken houses that routinely give me high levels of salmonella. This, in the long term, can give us a learning experience of what are we doing that is lower in that contamination level, what are we doing that is giving us good farms, and what is happening in some of the farms that are giving us trouble, either biosecurity failings, maybe wet bedding, some of the things that we know that could contribute to higher levels of salmonella, and that we can intervene in those farms and maybe process them in a customized manner at the plant. A new approach that we're using, and we recently published studies like this, we're looking at not only the box plot, but also the distribution of the data. And this chart has been published recently. We use the data from a prior study and look at what we call kernel density charts. So you can see this is the different locations that we saw before, the biomap that we saw before, with live receiving here. Look at the very nice variability and distribution of the data on the live receiving side. That's why we believe that if you develop a baseline for your farm and you develop a data collection like this, if you have an intervention, for example, that is reducing the levels of salmonella at the pre-harvest site, you should be able to see it here because we will show differences, a statistically significant difference with this treatment. So that's one approach we're looking with Alura to work with. In this study, we were also able to see this effect. Can you see this bimodal distribution effect in the low chemical site? The interesting thing about this one is that we noticed that there was a distribution higher on the second shift and a lower distribution of levels in the first shift. So that's showing the cumulative effect of the shift on the levels of contamination in the facility. So notice that in the facility with the chemical, when we use the chemical interventions at the regular levels, you don't see that much of this bimodal distribution in the red distribution chart, but you can see it in the blue side. So this is what we used to call this the naked process with low levels of chemicals, so you can see really what is going on without the chemicals hiding the actual levels of contamination that we have in the facility. So you can see that the chemical interventions tend to show more data points in the lower end range of the samples that we have. So this paper has also been published. So you can find it in the literature. With Campylobacter, we also have this distribution. Notice that we have a wide distribution on the live receiving, not as nice with as the total counts. But then you can see you don't see that much of effect of the shift effect on the Campy side, but you can see that the levels are being reduced throughout the process to less than 2 logs, 1 log even in the post-chill samples and the wing samples at the end. This is why we hear from the industry sometimes that we believe that PDA doesn't do much Campy, but the reason why we explain that observation is Campy arrival levels are around 5.5 logs of Campy. So even if the process kills about 5 logs of contamination, you're still going to have 0.5 logs of it that could be detectable. So if you're using just prevalence as your indicator of Campy, you are still going to see presence of Campy at the end, But in reality, we lower from high levels of contamination incoming to the plant to very low levels in the whole carcass and wings and parts area. Whereas Salmonella, you start with 3 log levels of contamination incoming, and then the process could reduce 2, 3, 4 logs of contamination, and therefore you have very low levels of detection or very low levels of quantification with Salmonella in the plant. More recent studies, we haven't published this, so please keep this confidential, but we're starting to compare other shifts. This is another facility where you can clearly see the difference between shift 1, cleaner facility, with shift 2 comparison. This is another study where you look at it. You can see the post-chill samples here, and then we have wings before and after treatment, and then tenders before and after treatment with a chemical intervention. These studies were looking at the means for statistical significance in between the shifts, and we can see a statistical significance between shift 1 and shift 2. We're also using this testing to look at the flocks. So you can see flock 1 all the way to flock 10, live receiving levels of contamination with Salmonella and rehang levels of contamination with Salmonella. In general, we can come up with 2 tasks after looking at this data. This is very limited. It's only 5 to 10 samples on a location. We need to build up more, but even with that, you can still see some trends. You see a flock with a high level of incoming Salmonella giving me a high level of rehang levels of Salmonella. Therefore, we'll have to work more with the interventions in the facility. But then when you have levels of very low levels of contamination coming with the live receiving with a flock 4, then you have very low levels of rehang contamination in the plant. So this is giving me hope that definitely there's opportunities for live receiving and rehang, and then looking at the flock treatments or maybe management at the farm or interventions at the farm where we can lower that incoming load. They could translate into lower levels of contamination in the process itself. So again, this is underdeveloped. This is fresh new data that we were analyzing and we'll be publishing soon. At the level of the industry, we're looking at how do we develop a statistical process control and where do we look at those differences. So one of the approaches has been to look at the reduction achieved between the rehang location and the post-chill location to see the statistical variability of that reduction itself. So you can see this data here. This is rehang data collected in a facility and the levels found of Salmonella in the post-chill location. So in this place, you can see that we start with a 2 log level in the rehang, and we end up with a 0.3 level in the post-chill location, giving us a 1.78 reduction. So all the data points that you collect before and after rehang and post-chill can give a reduction of the process itself, and you can look at the variability of that reduction and then use that variability of the reduction as your statistical process control for component 2 of the new incoming regulation. But we also wanted to look not only at the difference between the rehang and the post-chill location, but also at the difference between the rehang and the parts location. And here you're looking at, in the above charts, you see the reduction between the rehang levels and the wings location without treatment. And on the right side, you see the wings with the treated wings for a reduction of 1.2 without the treatment and 1.8, 1.9 logs with the treatment of the wings. Similar thing we see with the tenders at the bottom, with a 1.7 reduction without the treatment of the tenders, and then with a 1.85 reduction with the treatment of the tenders themselves. So we're going to be using this data for statistical process control, and I'm going to have a more complete presentation during IPPE for some of the industry partners. So at the end, where are we looking? We're going to close here. What are we looking at? We're looking at a new performance standard. The premise of the standard is looking at quantification levels of Salmonella, maybe an upper threshold of 10 CFU per mil of rinse, which that is the level of quantification that we have with the current methodology. Then we're going to look at intensified sample. If your samples are above this threshold, maybe once or twice to increase that sampling number of samples to see if you are above that threshold. If your intensified sample determines that you are above that threshold, then you're going to have to look at serotyping or maybe looking at gene virulence genes location, looking at the KPIs, the key performance indicators of pathogens that USDA is deciding which ones are going to come up. And finally, if you are failing your higher levels than 10 CFU, and then you're having the pathogens that USDA will consider as KPI, that may become an issue with adulteration. Maybe you'll have to make a decision on product disposition. The logistics of implementing these standards are going to be challenging, but this is a discussion we're going to have probably this year for implementation. What is our goal at the end of all these studies is to include this collection of data and use the new tools, new technologies like machine learning and artificial intelligence for helping us make decisions. So in the past, we collect the data, we look at the data manually and make decisions based on human analysis. We used to describe what happened after the fact. And with that description, with that learning, we make decisions and take actions. We can now create a diagnostic of the process to find out why it happened, the root cause of why it happened. But we can take it beyond that. And if we collect sufficient data, we can start predicting what could happen when some of the variables are in place. If we're getting this level of contamination at the farm, what kind of levels I'm expecting to have in the final parts and cold carcasses in the plant. So we can predict that. But at the end, where we want to go is actually with prescription, not prediction. We want to know, what can I do to prescribe a process that at the end will give me the levels of contamination that I want, that I can manage. So those decisions can be made by supported decisions with the data we collect, or we can make those decisions with autonomous systems where a computer is trained to find out which flocks are coming, what farms are coming, what levels of contamination are coming, what kind of levels of intervention should I apply in the process, and that will prescribe how much do I need to treat that farm so that I can get a product to comply with the regulations itself. So that's all I have for this presentation. This all is based on the traditional continuous improvement system that look at defining what we're looking at, measuring with biomapping to determine the prevalence of contamination, analyzing the data, the baselines to find out the root cause, the deviations, solutions, improving the process with interventions, with control measures, with validations, and finally establishing an ongoing monitoring system for statistical process control. So thank you very much for listening today, and I'm open to some questions.
Thank you very much, Dr. Sanchez. We actually received some questions. So I'm going to start reading them. You showed that there is a poor correlation between indicator organisms and Salmonella. What about Campylobacter? Are there any indicator organisms that correlate well with Campylobacter prevalence?
Okay. If we look at just prevalence of Campylobacter, as I was saying, since the carcasses are coming loaded with Campylobacter, even though with the reductions, we may still see some levels of prevalence at the end. Unfortunately, Campylobacter, actually, because of the unique nature of the organism, we have the industry has developed specific methods for Campylobacter. So, for example, the papers that you saw here were done using a high throughput quantification of Campylobacter method, and that is straightforward. It's the same as you doing an indicator. So I haven't seen any direct correlation between the indicator and Campylobacter, but because we are able to, on the same sample, run Campylobacter quantification and prevalence with the same easiness, even better than Salmonella. The challenge with Salmonella is that the level is so low that some of the methods lose it in the quantification level. I see another one in the chat from Mark. He's asking if you sample the same house multiple times for Salmonella, how much variability would you expect? When we did this with prevalence, we saw some variability, but I would say that a good 50% of the chicken houses had a trending behavior. Therefore, if half of the houses show me a trending behavior, I mean, the bad ones tended to be bad over time, and the good ones tended to be good over time. Now, I would love to develop a system like that. That was a 3-year study. We are just starting with studies with quantification at the farm. So I don't have that data yet. But I would believe that we will have a similar trend. You may have chicken houses with a consistent level of contamination if you're using the same treatments, if you're using the same breed and production practices, of course. And you can see that trend at the farm. Not perfect. This is very noisy. That's the power of a lot of data. When you have a lot of data, you can see the trends. If you have very limited data, you're not going to see any trend. But I would believe that a 50% trending behavior will be maintained if we look at quantification of salmonella. Again, it's a speculation, but from what I saw with using prevalence data, I think that will be the behavior with quantification.
Perfect. Thank you very much. We have another question. In your experience, which pre-harvest interventions provide the best reduction of salmonella? Non-vaccinal or vaccinal interventions?
I believe that the perfect example of how vaccination can help, maybe the levels we don't know, but at least the serotypes of concern. When you definitely target a particular serotype of concern, you can have cross-reactivity. And the Heidelberg example is probably our best case study, where we had an issue with Heidelberg. We targeted that with a vaccination pre-system that was cross-reactant, and then we were able to control that. Unfortunately, we didn't quantify at the time. We didn't have the tools for that, so we didn't see the effect there. But I don't have a perfect tool. I believe vaccination is probably the way to go, supplemented with maybe some diet, nutritional enhancements that may improve the immune system of the animal, maybe the digestive tract of the animal, so that we can have better systems. So I guess that's the area where we are definitely have opportunities to explore now that we have better tools for quantifying and for serotyping the isolates that we have. Yeah.
Perfect. Dr. Marquez, we have two more. Thank you, Dr. Sanchez, for the presentation. Do any of the facilities you work with add microbial in their scalders? In your opinion, is there value in scalder additives as a salmonella intervention?
I remember we started that approach in the early 2000s, and then we dropped it. We didn't see much value there in the scalders. I believe there is an opportunity. Why? Because that's the place where we actually set the contamination after the opening of the follicles of the feathers, and that's where the contamination can enter the carcass. So if we develop, it doesn't necessarily have to be a chemical intervention. It may be a physical intervention. What if we come up with a system that we wash out some of that contamination that is just about to attach to the follicles in that area? So I believe there's opportunity, but I don't have a perfect intervention at the moment for scalding that will give us the value that it could be measured later on. I haven't seen it yet. I know we have a lot of chemicals that allows us to get a better defeathering process, but I haven't seen it. So if there's anyone, I would love to test it and run it with this biomapping system, because we should be able to see the impact of that intervention in the system. Yes.
Perfect. And to finish, we have much work on antimicrobials is done in second processing. I am curious if there are opportunities to do in first processing to reduce loads prior to rehang and address salmonella internalization in skin.
Yes, I definitely we're looking at some approaches. Either there's some new technologies that are being presented in the last couple of years. Micro droplets, electrolyzed systems of dispersion of the either water systems or chemical intervention. So there could be opportunities. I am looking forward. I'm discussing with some of the industry suppliers to work on validating some of these approaches. So I believe there's opportunities there. I haven't done it myself, so I cannot recommend anything at this point. But definitely, if you're able to cut down those levels that we know are high in the scalding and the feathering area, and you have a lower target with the interventions later on in the evisceration, then you definitely should be able to have more negative samples or more samples under the quantification level. And if you're under the quantification level, remember, if the new standard comes up with a 10 CFU per mil upper threshold, then you'd be in compliance. So that's definitely something that we want to look at.
Thank you again, Dr. Sanchez, for the excellent presentation and sharing your knowledge with us. It was really interesting to hear. And we also would like to thank the attendees of the webinar today for taking the time to listen to our presentation, and all our colleagues in the background helping to organize this webinar. Please keep in mind that we have one more session coming. Our next session will be on February the 8th at 9 a.m. Eastern Time, and we'll have Dr. Admik Murray bringing us knowledge about harnessing the power of artificial intelligence.
There's a hand up, Eric. How you doing, Eric? Do you have a question? Eric, go ahead.
Just give me
okay. So you have
1 second.
Yeah, he's having an issue with the
Okay.
Allow him.
Yeah, I allowed him to talk now.
Okay, try talking now, Eric.
Okay, good morning. Can you hear me?
Yes, we can hear you.
Yes. Okay. Thank you for that, and Dr. Sanchez for your presentation. Those the two questions that you addressed about scalders and first processing were my questions. So you thank you for your thoughtful response, and that's an area that we're very much so looking at here at Butterball. So I'm going to be at IPPE as well, and I'll definitely be following up with you and see what we could potentially do in first processing.
Awesome. Yeah, very interested in that. So,
okay. Thank you.
Thank you very much.
Thank you, Eric.
Well, thank you very much, Dr. Sanchez.
Okay, thank you all, and thanks, Alura, for the invitation. We'll continue the conversation and in Atlanta, I guess.
Of course we will. Thank you very much.
All right. Thanks
Have a good
again.
day. Thank you.